The things we buy serve us for a time and then wear out, no longer do the job they were intended to do. The life of a product will vary by product design and quality, the environment in which it is used, and the rigors of the task it performs. Often, the original cost of an item is a poor measure of its economy. Service life is probably the most reliable measurement. In general, the service life of any product is the length of time it will perform the functions it was designed for: cleaning your teeth, keeping your feet dry, altering the temperature of a product, and so forth. Steam traps are designed to maintain the operating efficiency of a steam system. There comes a point in their life when their performance results in an unacceptable product, or they consume enough energy by passing live steam that it is cheaper to replace them. The true economic value of a trap, then, is its original cost, the energy it consumes to do its work, the maintenance and downtime costs during its service, and the parts and downtime costs for replacement. It naturally follows that the most economical trap is one that functions properly over a long period of time, saving energy and eliminating high costs of frequent repair or replacement. Drip and tracer applications employ more steam traps than any other, so a great deal of energy and money can be saved here. Since disc traps and inverted buckets are the most prominent traps for drip and tracer applications, it seems wise to compare them, observing how their designs and principles of operation affect the service life of each. First of all, the traps operate on two different principles. The inverted bucket is controlled by the difference in density between steam and condensate. The closing force is the pressure inside the trap less the pressure in the return line. The opening force is the weight of the bucket less the lift of the gases beneath it, multiplied by the mechanical advantages of the lever. The disc trap is controlled by velocity changes of the steam and condensate surrounding the disc as they change state. Condensate passing into the control chamber drops in pressure. If the condensate temperature is sufficient to reach saturation for this reduced pressure, some of it flashes into steam, increasing in velocity and decreasing the pressure between the disc and seat. Simultaneously, steam and some condensate collect above the disc, increasing pressure there. This differential pressure snaps the trap shut. Radiation condenses the steam, which acts on the total area above the disc. When this force is overcome by the line and back pressure operating upon the smaller areas of the inlet port and discharge groove, the trap opens. Because of its principle of operation, the disc trap must pass a high-velocity biphase mixture. In the inverted bucket, any steam is condensed by the water seal. Only condensate passes through the valve at a relatively low velocity. The inverted bucket forms a better seal than a disc trap because it has a much smaller seating area and a higher differential pressure holding the valve closed. The valve of an inverted bucket is pushed upward toward the seat by the bucket. As the orifice is restricted, the increased condensate velocity pulls the valve toward the seat, where it is closed by differential pressure. This is a much more gentle closing action than the disc, which is buffeted to any angle by the incoming condensate and then snapped shut as that condensate flashes. The velocity of this flash steam and the condensate, air, and dirt it carries with it erodes the valve and seat of the disc trap. The relatively low velocity of the condensate which passes through the valve of an IB causes little erosion. Obviously, the design of the valve and seat itself affects the wear characteristics of traps as well. The inverted bucket's free-floating linkage, hemispherical valve, and square-edged orifice provide line contact in any position. The valve is free to close in many positions because the lever is secured by a linkage which employs no fixed pivot points or guide pins to wear out. Long life is further ensured by using a seat material slightly softer than that of the valve. This difference in hardness allows the combination to be self-lapping, guaranteeing a tight seal over a long period of time without any adjustment. By contrast, the disc trap requires near-perfect flatness of the disc and both seats in order to seal. Uneven initial contact between the disc and seats causes wear of the sealing edges and disc surface. This wear and erosion of the disc and seat accelerate once started, compromising the ability of the trap to perform. In 1974, Armstrong began a program to test the degree to which the operation and design principles affect the service life of the two trap types. Disc and inverted bucket traps used in drip and tracer service were supplied for testing by users from all over the United States and Canada. All the traps were functioning when pulled from service, and the installation date of each trap was known. The traps were tested in our laboratories for the heat loss due to the traps themselves, the combination of both radiation and live steam losses. Test conditions were typical of tracer lines: 50 pounds per hour condensate load, 150 psig inlet, and 0 psig outlet pressure. The results were then plotted on a graph of heat loss in pounds of steam per hour equivalent against the time in service of the trap. After accumulating and plotting the data for hundreds of traps and thousands of tests, the average service life versus heat loss curve for each of the two types of traps was drawn. These curves graphically illustrate the difference in the energy efficiency and service life expectancy between the disc trap and the inverted bucket trap. Most drip and tracer traps lose about the same amount of heat when new, the equivalent of 1 to 2 pounds of steam per hour. The average disc trap wears rapidly, especially on light loads. The wear increases dramatically with time. The inverted bucket trap's wear is significantly less. Its curve indicates a low energy usage and a life expectancy well beyond 5 years. When a low-capacity trap begins to lose more than 10 pounds of live steam per hour, the high cost of energy dictates its replacement. On identical applications, a typical disc trap would need to be replaced 2 to 5 times more often than an inverted bucket to achieve a comparable steam conservation record. The cost difference in wasted steam alone can amount to thousands of dollars a year after only 2 years. Add to that the costs of downtime, replacement parts, and installation, and the dramatic difference in service life becomes a dramatic difference in cost. In a study documented in a 1983 issue of the Armstrong Trap magazine, Schenectady Chemical Company at Freeport, Texas, proved the wisdom of the use of inverted buckets on tracer lines. Of the original 1,043 Armstrong 1010 stainless steel inverted buckets installed in 1975, only 48 had failed. That's 95.4% of the original inverted buckets operating reliably and efficiently after 7 years on the job. That's service life. And the greater the service life of your trap, the lower its cost to you.